without further ado, let's dive in. Let's see. All right. So we are going to try to answer these questions today. This workshop covers the fundamentals of relational database management systems and what problems they solve. And I won't read this slide, but I'll keep it on the screen for just a second or two so you guys can read it. But the first half of this workshop is going to be actually building a relational database. So we can use SQL to query that. So the first part is building the relational database, and then the second part will be using SQL to query that. All right, so what is a relational database? Well, I went out and scoured the web for good definitions, and I found this. I don't like it because it uses a lot of the words that it tries to define in the definition. Further down in the Wikipedia article, it says this, which is kind of more descriptive, but not really. Like what is relational data, and what's a table, right? And so I think the best way to describe these concepts is through an example, which is what we're about to do. All right, what is SQL? So relational databases and SQL are two different things, actually. They're related, but they were invented separately. Going back to this slide, you can see that relational databases are over 50 years old, and they are a concept. The concept was an academic paper by Mr. E.F. Codd, or Dr. E.F. Codd, rather. He published that paper in 1970, and they've been using relational databases ever since. Yeah, so SQL came about shortly thereafter. E.F. Codd published 12 rules for relational data integrity, and then didn't develop a system of how to access that data. So shortly afterwards, some other smart people at IBM introduced a handy syntax to query data from relational database management systems. It's SQL or SQL. I've heard both out in the wild, so you can use either. In fact, I don't even know which one I'm going to use. Find out. All right. So relational database is a conceptual framework, not an implementation. So we need software to make a tangible, concrete implementation of that framework. And so there are many, many options, both in servers and clients. So the implication here should be it's a server client protocol. So you start some process out there in the cloud on a server somewhere, or even on your computer. You can install any of these on your computer. And then you use a client to access it. All right. And so these are some of the more popular ones. We are going to be using MariaDB today. It's one of the more popular ones, and the one that we actually run in production for our systems at the RCC. If I were starting from scratch, if I was going to advise somebody starting from scratch, it would be probably recommend Postgres. But there's a whole bunch of SQL compliant databases. On the client side, you can see that Microsoft Access is on both sides because it is actually used to be a program that you can install on your computer that was bundled with Microsoft Office. And it was kind of like a Frankenstein app. It implemented some SQL, but it was just an attempt to be a point-and-click database. I think it still exists in some form or another. It's probably in the cloud now, like everything else in Office. We are going to be using today HeidiSQL as the client. It's free and open source, and so you can download it. If you're running a Mac, I highly recommend SQL Pro as an alternative. But you don't have to use any of those tools today because this workshop is not interactive. All right. So regardless of whether you have both the server side and the client on your computer, it's still a client server protocol. Okay. All right. Now let's start building a relational database. So I'm going to reset my timer here so I can just stay on track. All right. So what do we need to do to have a relational database? Well, we need a business problem, right? We need to have a use case that we can solve. And so what I usually do is try to define the use case in plain English. And for today, we're going to introduce the concept of a restaurant. Right? So XYZ restaurant has a need to track customers' names, email addresses, birthdays, and favorite dishes. So at this stage of the process, my preferred tooling is analog. Now, I'm not going to use analog today because we only have 90 minutes and I value your time. So we'll use digital tools instead. But really, in this phase of the planning process, I like to use paper and pencil or a whiteboard because I'm going to be iterating a lot on ideas. All right. One other thing that is required is to keep it simple to start. We don't need to add any premature complexity. In fact, complexity is the enemy at the step of the process. So we'll start with the tools that most everyone here is familiar with, a spreadsheet. All right. So I'm going to be flipping back and forth between the slides and the sheet a lot. All right. So what are the what's the primary noun in this sentence?
Restaurant.
Restaurant, yeah.
Capital R.
So it's got a capital R. That's a good thing. But what are we actually tracking? Customers, right? Customers. So let's build a table or a spreadsheet and call it customers. All right. So I'm going to rename sheet 1 here. Customers. All right. And now we're using a spreadsheet, which I'm going to start off using. I see that we need the names, email addresses, birthdays, and favorite dishes. So I'm just going to make those columns. Name, email address. Now. Birthday and favorite dish. Okay. All right, so that is our data model to start with. Simple, concise, no extra stuff needed. All right, we're gonna populate some rows of data here. Just so bear with me. Amy Steak, Amy Steak at example.org, and her birthday is 2001. 03 dash, and her favorite dish is pizza. Lee King at example, and his birthday will be 1981. 5/18 or 15 or whatever. And his favorite dish will be chicken. And finally, Barb Dwyer, B. Dwyer at example.org, and 1995-04-05. And her favorite dish will be fish. And let's just add one more person, another Lee King. And his birthday is 1991-05-16, say, and his favorite dish is also pizza. And then I want to add one more person, bear with me. And then we'll call her birthday 1991 too. She shares a birthday with Lee King. All right, so we got the data. We got data work. Oh, sorry. All right. All right, here's our database. All right. So have we covered all the bases? Names, email addresses, birthdays, and favorite dishes? We have. All right. So What I want you to notice there now is there are two Lee Kings, right? Are these the same person? Is this a data entry error? How do we know? Well, we have clues. First of all, this Lee King has a different email address than this Lee King, and they have different birthdays. They were born about a decade apart, and they have two different favorite dishes. All right, so we'll just assume that these are different people, but how do we tell the computer that? All right, so we're using a spreadsheet, right? And unbelievably, spreadsheets were invented after RDMS was postulated. So relational databases actually came before spreadsheets. Relational databases came in the 70s. Spreadsheet, I think the first spreadsheet software was introduced in the early 80s. Don't quote me on that, I might be correct. But we have a handy tool in spreadsheets that we don't have in databases or relational databases, which is automatic numbering, right? You can see that Lee King is on a different row than this Lee King. But in the databases, we don't have it. And so what's the solution? Well, we add a column for identifying each record. And I'm just going to make 1, 2, 3, 4, 5. So if we added another record to this database, it would be 6, right? ID 6. 7. All right, so this is what's called a synthetic key. And it also happens to be our primary key. Now, we could have named this key anything we want, like SDF. I'm just sticking with a naming convention, ID. It's what's known as a synthetic key or a surrogate key because it has nothing to do with the other data in this record, which is the ideal use case for us. In other words, anything about this record, this human being is represented by AID1, and she can change her name, get married, right? Email, she can choose another email provider. Maybe we entered her birth date wrong in the data entry, and we need to correct it. And maybe she decides that she doesn't like pizza anymore, she likes fish, right? Anything that can change about this record, but the concept is this is one human being. She's not changing her identity. When she walks in, she's still Amy Steak, right? Regardless of what her name is. So that's what data integrity means. This one concept or noun in place and time in the universe represented by this record in our database, by this primary key. All right. Let me just see if I've covered everything in this slide. Yeah. All right. Now we're going to discuss some terminology differences between spreadsheets and databases. So if I added another sheet to this database, or this spreadsheet, this workbook, let's say all right. These two spreadsheets together would represent a schema for a database. Each individual sheet is called a table. So customers and foobar are each tables in our database. Each row, well, they used to call them tuples, and some people still do, but I prefer record. That's more intuitive. So each row is called a record. And then each column is an attribute in RDMS land. And finally, each cell is a field. So person with ID 3 email address is B. Dwyer at X-Sub. Now, in common vernacular, we can say tables. Tables is used, but I've heard columns and rows be used to describe database records as well. In fact, you might hear me say that because I talk about them so often. All right, we're going to make some changes to our database schema now. So make this more computer friendly. So these names are human friendly. These column names, these attribute names, ID, name, email address, birthday, and favorite dish. But computers abhor space carrier. So we're going to just remove all our spaces and make it all lowercase. And I'm going to use this naming convention consistently across all of my tables in my database. In fact, email address is kind of implied. So the address part is kind of implied. So I'm just going to call this column, this attribute email, birth date, and favorite dish. So I'm going to put underscores, substitute underscores for everywhere I have spaces. All right. All right. Now these names are more computer friendly. And that'll make a difference as we'll find out when we actually start working on our database. All right. The key takeaway from this is every record should, in every table, should have a surrogate/synthetic key. And it should be arbitrarily non-related to any of the data in that record. Most commonly, it takes the place of an arbitrary integer. And a lot of database tooling gives you shortcuts for making IDs for records, and we'll see that in the coming moments here. All right, so let's review what we've learned so far, and then I'll take questions if there are any. So terminology review, attributes, records, primary key, table, and field. All right. Any questions so far? Any questions on that? Okay, let's move on then. Now, let's throw a wrench into our works here. Let's say we want to rename a dish. We want to rename pizza to Super Duper Pizza. We're offering a brand new pizza on our menu. And so I could rename it manually, but let's just pretend I had, a couple thousand records here for customers. That's ideal. We got a lot of business at a restaurant. Good. So I'm just going to go to my handy dandy search and replace tool and replace pizza with Super Duper Pizza. And replace all. Done. All right. You see what happened here? What happened?
Oh, Wanta got married.
Avanta. It changed Avanta's last name. Oh my gosh. Let's undo that. All right. So how do we solve this problem, right? This is where get into a process called normalization. Now, to further drive home my point, let's say we want to track not only dish names, but also the prices. So dish price, I'll say. And pizza will be $5, chicken will be $6, and fish will be $7.50. And we'll just copy and paste it for every row. All right. But what happens if I have thousands of records and I want to change the price of pizza? Well, let's just pretend that chicken was the same price. So search and replace wouldn't work here, right? I can't just find all the 5s and replace them with 6s unless I want to increase the price of chicken too. So how do we fix this? Well, this is where we stop and ponder because we are repeating data. Pizza, pizza, pizza. And so this is called what's called in programming. How many people are familiar with programming in here? Have at least cursory introductory level? Okay, so not many. This is called a code smell. And you should take a step back and wonder, okay, how do I fix this redundancy here? And so what we're gonna do is add another sheet. And we'll use that to track our dishes. All right, the first thing I do when I create a new table, I create an ID column. Right, or an ID attribute. And then what do we need to know about our dishes? Ooh. I knew I was gonna do that. All right, well, we have the name and the price. So let's just 2, 3, pizza, chicken, fish, and then 5, 6, and 7.50. All right. Now, we've got one table that tracks dishes and one table that tracks customers. So we need to find a way to replace this with a reference to dishes table. So I'm going to add another column. And I'll just say favorite dish. And then I'm going to refer back to the identifier for this table. So pizza, I'm going to substitute every instance of pizza with 1. Pizza, pizza, pizza. And likewise, chicken with 2 and fish with 3. All right. Now, I know that in this table, ID 1 is equal to pizza. So this customer's favorite dish is pizza. That makes these two attributes redundant. And so I can delete these 2 columns from my sheet now that I have the reference to the other table. And then I can manipulate the price of whatever dish I want, right? So let's say inflation happens and I have to double the price of pizza. Well, I can do that, right? Because this is what is known as data integrity. So if you have a lot of rows with redundancy in them, you should stop and take a step back and be like, oh, maybe I need a new table. Maybe I need to normalize this data. Now, this column here has a special name because it's a reference to another table. It's called a foreign key. Foreign key. So we have primary keys that identify the records in the table, and we have foreign keys that identify records in another table. In this case, the foreign key in the customers table references the ID attribute in the dishes table. And so I like to name my foreign keys descriptively. So I'm going to say favorite dish ID. Why do I do this? Well, it immediately foreign keys jump out of my schema at me. I'm looking at a diagram in this scenario. So like, and I would name it foreign favorite dishes ID to keep the table names consistent, but that doesn't really make sense in the context of a favorite dish, right? Customers can only have one favorite dish in our data model. And so I'm just going to leave the dish singular, and it should be enough information to let me know, okay, this is the primary key in the dishes table. Any questions at this point? All right. Let's move on then. What we've been doing is called normalization. And this is the definition, but it's really just simplifying or organizing your data to minimize redundancy, the key here, and improve data integrity. And you should get, if you eliminate the redundancy, this comes automatically out as a bonus. Integrity is. All right. Okay, so let's review our database schema right now. So we have customers, and this doesn't match the data. This slide doesn't match the data in our actual database. So don't expect anything to be consistent here. But the concepts are the same. We have a primary key ID, and it's an auto incrementing integer. We have the first name and last name. Oh, right, yeah, so hang on. What if I want to sort by customer name, right, in the future? Just get a list of all my customers alphabetically. Well, I can do that by first name right now, but not last name. So that tells me I need to break the names up into their component parts. So Amy, steak, Lee, King, Barb, Wire, Lee King again, and then that pizza. All right. And see here how I've substituted the underscores for spaces. Again, that just makes things a lot easier to avoid spaces and names and attribute names. And we'll see why in a minute. All right, so we have first name and last name. And we have 3 dishes. So inflation has already happened on this slide, so it is now $10. We'll say it's a whole pizza though, for the whole game. All right, so at this point, are there any questions? Yes.
Is that okay to have the same like ID on both?
Oh, good question. So the question was, is it the same, is it okay to have the same column name on both tables? And the answer is emphatically yes. In fact, I would recommend you choose a single name for the attribute that is going to be your primary identifier. I like lowercase ID, and then stick it with it for every table in your database, unless there's a good reason not to do that. But I have not encountered one yet in my 15 years of working with databases. So yes, that was a very good question. The reason is that the database engines all know that dishes ID is different than customer's ID. It's actually a fully qualified name and it includes the table, and we'll see that when we start to work in SQL. All right, so at this point, I'm going to actually drop the spreadsheets and then open up my Heidi SQL client and show you where about how this is implemented in an actual database. So I'm going to switch over here to my Heidi SQL client. And to save time, I've obviously pre-populated the data here. And so we've got 26 customers in our customers table. And where's my mouse? There it is. 3 dishes. And we see here that we have column names the same. So this is a MySQL client. It is free and I like it a lot. I've been working with it for a while. Let's see. Notice that the tables are all over here listed on the left. I've got my IDs and the Heidi SQL client just shows me this gold key for the primary key in every table. And I've added a state, which we'll use, our state attribute, which we'll use when we start to work with SQL.
A quick question.
Yeah.
How does the client know what your primary key is? Like, do you tell it or do you load the table in and it just like figures it out?
So the question was, how does my client know what the primary key is? We actually configure that when we're building the table.
Okay.
We'll do in a minute.
Okay, gotcha.
So that's a good question too. Keep them coming. All right. All right. So, oh yeah, and this favorite dish ID is a foreign key. All right. All right. So I'm going to switch over to another tab here to talk about data types for a minute. So we have our columns here listed as rows, but in the actual data view, they're attributes. So I'm going to refer them to them as attributes as best I can. And see first name, last name, last name, et cetera. You can see that there's a data type defined for each attribute though. And so ID is our primary key, and it's defined as an integer. And you should know that an integer means number, right? In fact, integer is a special kind of number, one without a decimal, so whole number. And first name is text, right? We're going to enter text for this field. And in database RDMS systems, it's called a varchar. Now, as you can see, there are multiple kinds of text fields, and we don't have time to get into these today. But varchar is what you want to use unless you are storing long paragraphs of text, in which case you want to use text. And see here how I hover over the data type and it gives me an explanation. That's really handy. That's Heidi SQL doing its magic. Other database clients are different. And then birth date is a date. Temporal fields, there's a lot of different kinds of those. And there's a date time and a date. I picked date because we don't really need to know what time our customers were born at. And then favorite dish ID is a foreign key here. Notice that there's no denotation about it being a foreign key. We have a little gold key here for our primary key and nothing for our favorite dish ID that references the dishes table. Now we could set up a constraint in our database, but I don't want to get into that today. Basically, it verifies the data integrity by forcing this to be a valid record in this. So if I had data constraints enabled, I would say, okay, if I don't have a record with ID 1 or 5 in the dishes table, I'm going to throw an error, try to enter a customer that says that favorite dish. All right. This is not a comprehensive list at all. Actually, there are many, many different types, but these are the most common ones. And the difference between char and varchar is you have to specify a fixed length of characters for char. So, and that is how much space each record occupies disk-wise on the disk storage space for every single record. So if I said three characters long, ABC, it would require every record to store that amount of data regardless of what was in there. So I could just have a record with one character in it, like B, and it would still take up the same amount of space as if it was storing 3 characters. Now, in 2025, when storage is cheap and abundant, that's not a big deal. But in 1975, when people started building these things, storage was very expensive. And so like if you had a database with a chars in it, then you might fill up your data, right? So they invented a variable length character field, which is the one that is used most often these days. And it depends on the length of the string, and the database stores whatever the closest approximation in bytes to that is. And I'm kind of winging it here because I really don't fully understand this. But if you want an in-depth explanation, I can point you to resources online. But here we've been using varchar for all of our text fields. All right, and then there's a text field. So what's the difference between varchar and text? Well, first of all, I set a maximum length of 512 characters and 255 for the first name. So first names can only be 255 characters or less, and last names can be 512. That's on purpose. That when you add a record to a database, it automatically creates an index of that. And this matters if you have hundreds of thousands of records that you want to query later. If you set the data type as text, let's set the data type as text for last name, it has to read the whole text many paragraphs, possibly, potentially, if you have that data stored versus it indexes, care is a lot nicer. So if you anticipate querying your data based on that attribute, you should really try to use care. Integers are whole numbers, can't put decimal points in here. If you want to put decimal points, it's called floating point integers or floating point numbers in computer land. And so we use the type float. And these are, datetime is self-explanatory, obviously. And tiny int is just one bit of data, on or off, 0 or 1. And that's useful for Booleans, right? True or false. This user is older than 65. So they get the senior discount. True or false, right? Now we can deduce that information from the birthday. So we don't need a column like that or attribute like that. All right. And there are many more data types, and I regret the fact that we can't get into all of them today, but just know that, hey, columns have data types. All right. All right. Now let's throw one more wrench into this problem that will allow me to show you how to create a new table. Events. Let's say our restaurant wants to host events. And so we have another sentence in our problem statement. XYZ restaurant also hosts events and would like to keep track of names, dates, times, and contacts for events. All right. So I'm going to make the assumption that, first of all, the key noun in that word is there are sentences and events, right? I'm going to make the assumption that our organizer / contact is already in the customers table or will be added to the customers table when they come in and say, I want to host an event. Because the customers keeps track of people. And what's an organizer? A person, right? So we don't want to recreate the wheel and add extra redundancy to our system. All right, so let's create an events table. And this probably will answer your question about the primary key. And so to do that in our client here, I have to right click on the schema and create new table. All right. And I will give it the name events, keeping all the table names lowercase. Now, if you wanted to stick with a naming convention that says uppercase letters for the first part of a word, be my guest, but I prefer lowercase. Also, in terms of naming conventions, you can see here that I'm keeping the plural singular consistent too. So events versus event, customers versus customer. It doesn't really matter. Everybody has their own personal preference, but you really need to keep it consistent. That's the key. All right, so let's add a column. And I will say ID, because we always start with an arbitrary identifier, right? And the data type is already integer, what I want. And then we won't fill in the linked set field or attribute for this this column. For this, I'm getting my names confused. This is an attribute that we're adding. These are the properties of the attribute. All right, I'll explain what unsigned is later. This is disallow null. What do you think this does?
Doesn't to be empty.
That's right. Do we want a record with an empty primary key? Probably
shouldn't. It's a bad idea.
Definitely should not. So let's uncheck that. And then I'm going to come over to the default here and see, okay, this is interesting. So I told you that the database engines typically take care of IDs in the background automatically for us if we configure it to do so. And so we configure the default to be auto increment in this case. And so what this will do is that it will increment the highest number record for every record I add. So if the first ID should be 1, right? And the second ID should be 2. And the third ID should be 3, right? And then the database automatically takes care of that. So let's just set that to auto increment. All right. And these, everything past comment here is out of scope for today. Let's just keep adding columns. All right. So what other columns would I like to have? Okay. Name of event, right? Name. Now I could put event underscore name, but the table is going to be called events. So I'm just going to say name. And what's an event name? Well, it's a text. So I'm going to say varchar, and the default is 50. That means so this is something to think about. If we want event names to be able to be over 50 characters, we should really change the default, right? So I'm going to assume that we do. I'm going to just put 512. All right. Why not 500? Well, this goes back to, we could put 500, but I like to do multiples of 8 instead. It's just a computer thing. And then default is 0. I don't know what IDSQL is doing there, but I think we should force the people to enter an event name. So no default value. Now, should we allow events without names? Probably not, right? So we're gonna keep the allow null unchecked. All right, date time, right? Date time. All right. Now, go down to our temporal fields. All right, we got date, time, year, date, time, and timestamp. I'm not gonna go into the details of each one of these data types because you can look that up on your own time. I will say that if I'm tracking only dates, I use the date field. But I think event time should be tracked too, right? Because there can be multiple events on one day. So I'll choose the date time field for this. And again, we don't want any default value. And do we want to allow this to be null or not? Now that's a business question. Because somebody could be coming in to our restaurant and say, I want to host a party. I don't know when the date's going to be, but we do need to record that in our database. So I'm going to allow that to be null. And finally, I didn't name the column. Date. All right. Finally, the contact, right? So we have an existing table that we want to keep track of contacts in, also the customers table. And so I'm going to say organizer customers ID, actually customer ID single. All right, this goes back. So this is going to be a foreign key. And the thing about foreign keys is that they have to match the data type of the column they're referencing in the source table. Let me just repeat that. Foreign keys need to match the data type of the data column or attribute they're referencing in the primary key table. Okay. Now in this case, I know what it is because all of my tables are consistent integer. So I need to make sure that this is an integer. And do we want to allow this to be null? No. Because a business rule is that human being has to be attached to an event. All right. Now, let's save this table. Unable to create or change table without a primary key. So we have to explicitly define our ID, which column we want to be our primary key. And we know which column, right? ID. So in IDSQL, we do right click on the column and set it to a new index. That's the gold key. You can see there's multiple different kinds of keys. Again, we don't have time to get into these, but you can definitely look these up on your own time. And save. There it is, my events table. Now let's flip over to the data tab, and it's empty. So let's add a record, okay? So in IDSQL, you do that by clicking this little green plus sign button. Now, We know that our database is gonna presumably take care of the ID for us, so we're gonna skip that field. Let's see, Halloween blowout. Right, and then it's gonna be on the 31st. And then I'll choose a random ID. All right. That's it. I just click outside of the row and you can see it automatically added the ID. Right. And let's add another event too while we're at it. So I'm going to skip the ID, say office party. It's fine. We'll set it for tomorrow and person number with ID number 6, whoever that is, to be organized. And so we have 2 events now in our table. Notice I didn't have to write any SQL so far. We'll get to that. Don't worry. What time is it? Oh, good. We're on track. So we have a Halloween party, Halloween blowout, and office party. And so who's the organizer for the Halloween blowout? Well, whatever person with ID 5 is, right? So we refer back to our customer. It's Lee King. And also Lee King, other Lee King is organizing the office party, but we know because we've got 2 records in here that they're probably different people. Lee King from Alabama is organizing the office party. Georgia is organizing the fall blowout. All right. So any questions so far? Yeah.
Not necessarily about just talk about, a little bit maybe. When you earlier showed, the different like servers and clients, you're working with all this data. I'm assuming it's not necessarily all standardized. So like you can't have, that's my question. Like, can you have a data set that you have and you use it like SQL Pro, you add onto your soft SQL server? Or
Ooh, very good question. Okay, so he's asking basically, if I understand your question correctly, can you transform or transfer data from one database engine to another product? The answer is yes, but it takes a lot of work. Because database manufacturers or software producers do not like you to move your database out of their product, right? If they're Microsoft SQL server, they want your money. And so, yeah, typically you can. That involves intermediary step. And you can kind of lose some information along the way. So each one of these engines, database servers, RDMS systems, I should say, implements the SQL standard, right? But they also have additional features on top of that. So, and I'll show you what some of those are in MariaDB here in a minute. But so this tool, this engine right here in MariaDB might have a different feature from Microsoft Access. And so if you want to move your data into Access from MariaDB, you might lose some functionality. And typically you need to export it to a neutral data format first. So like comma separated values, right? So that is the data format that you can dump data out into.
CSV files.
Yeah, CSV, exactly. And then try to re-import the data into another engine from there. But it really is a messy process. So you really ought to make sure you're choosing the right product for your database to live in forever. Does that answer your question? Okay, thanks. And we'll get back to where we were in the slides then. All right. Cool. All right. Yeah, so we're here now. Just catch up on my notes. All right. So we have customers, dishes. Now we have events. And this kind of is a diagram that shows the relationships between the tables, right? And so one customer can organize many events, right? So we've got customer number 2, Lee King, in our example diagram here, organizing 2 events. That's a possibility in a restaurant, right? Because we want multiple or a single customer to be able to organize multiple events, maybe even recurring events. That would be great. more money for us, hooray. So we call that a one customer and organize many events. That's called a one-to-many relationship. A common type of relationship in databases. Likewise, each customer can have one favorite dish, but one favorite dish can be assigned to multiple customers. So one dish can have many customer relationships, right? So that's also a one-to-many relationship. All right, is that clear? All right. That's a fundamental concept about relationships and relational data. This is our schema. 3 tables. We're off to a good start. And keeping it simple. So this kind of diagram has a name called an entity relationship diagram. And it's a fundamental tool in planning your data model. And most good database clients have them. Heidi SQL, I don't think has this functionality. But there's another database client if you're working with MySQL or MariaDB called MySQL Community Workbench or something. I don't know. They keep changing the name. It does have ER diagramming. And this is an example of one I found out in the wild. Hilariously, I think this is a video store. So this is very old. But this is kind of like what an entity relationship diagram looks like. Okay, and I know it's very small, and I will send out these slides to all the people that attended that signed up. Trisha back there. But you can see here that standard denotations. If you look really, really carefully, you can see the foreign key relationships. So city ID, and it's a small int, is references in the address table, references city ID in the city table. So they've normalized the cities and addresses into separate tables. Presumably because they want to run queries to see what customers they have in a city, right? They have that opportunity now. So this is just, I'm not going to get into this diagram. I just wanted to show you like what a real entity relationship diagram looks like. Notice that we have the data in ours, but we only have the attributes listed in the types in the real entity relationship diagram. And then it shows the relationships, which is kind of what you want to do, right? And so you can take a look at a diagram like this and be like, okay, this model looks good. Let me just implement it. And depending on your tooling, you can dump this right into this diagram, will generate this SQL commands to build this schema in a database. Kind of cool. All right. Any questions? Alex, are there any questions online?
Just one, can that screen be made larger? But it's.
Oh, yeah. Again, I'll send out the slides. All right. All right. So let's play some SQL now, huh? All right, this is what we came for, right? So there's obviously a lot more to database design than I was able to cover in that short amount of time, but at least we know what we're querying now, right? And how it's set up. So I'm gonna flip back over to my IDSQL, and I'm gonna open up the query tab here. And this is kind of how these kind of databases are traditionally interacted with. And so here I'm just going to try to recreate this view of my data, right? Like Heidi SQL automatically gives me this view of my data very neatly. But going back in time to the 1980s, I had to write a query to get this view. So here's what the query looks like. All right. When we want to get data out of a database, we always use the select keyword. Here's the same view, right? We play the query, we execute query, we get 26 rows, times 7 columns. And that matches pretty much this, right? Same with dishes. We want to get all the dishes. Right, that's pretty much the data in the data tab. Right. Interestingly, our SQL is case sensitive, so capital D doesn't match lowercase d. So that's by design. Because we could have a table, lowercase dishes, capital dishes. I wouldn't recommend that practice at all. Using, it is possible. All right, so let's dissect this query. We have a select statement here. What's this asterisk symbol mean? Well, by intuition, it means all attributes in this table. And then from